So I guess this is lecture 6, right? Yeah, yeah, lecture 6. And in this lecture, our goal is to study the contraction mapping theorem. The contraction mapping theorem, which is actually, should be a dedicated topic when we study metric spaces. But see, we are studying derivatives as linear transformations, right? And the linear transformations are being studied over Euclidean spaces, and Euclidean spaces are metric spaces. So in some sense, like, we are seeing that we have been using the notions of these Euclidean spaces being normed linear spaces, because when we were defining the derivatives, we had used essentially the norms on Rn and Rm, and we know that every norm induces a metric, or rather you just know now that a norm induces a metric. So the concepts of metric spaces and norm spaces are sort of entangled between whenever we are studying these derivatives over these spaces. And if you do not know what a metric space is, then you can think of it in this way, that given a set X D, so it's called a metric space. It's called a metric space if D is a well defined metric on it, is a well defined metric. What do I mean by a metric? So I am not giving out the formal definitions and the formal properties. Metric is just generalized notion of the absolute value on R, or rather of not directly the absolute value of the difference between the absolute value of the difference between two elements in R. Okay, that is exactly what we call the in some sense call the metric in R. Okay, so this is another intuitive sense should be that this is just the generalization of the distance between two vectors, or 2 points. Whenever we are talking about an arbitrary metric space, so we have a generalization of distance between 2 points. If we are strictly in the Euclidean space, then this is a generalization of distance between two vectors, 2 points. Let me just keep it points. Okay, this is exactly what a metric is, and the usual properties of a metric. So if I just, okay, let me just define on the usual properties. Firstly, that dxy is greater than or equal to 0 for all xy in X, and because the distance between 2 points should always be non-negative, that's quite sure, and the only possibility when they are when the distance between 2 points is 0, if both the points are same, right? And dxy is 0 if and only if x equals to y. Okay, now there is also something called as semi-metric, which is obviously not the not in this part. In a semi-metric you do not require this, that is if dxy is 0, then x must be equal to y. If both the vectors are same, then their distance is 0, but if the distance between two vectors is 0, we need not require them to be same vectors. But that is a weaker assumption than yeah, that's a more general case. That is something which we call a semi-metric, but rather leave it as it is. We don't require that in this way. Yeah, so this is the usual definition. So this is the first property. The second property is that the metric is symmetric, that is whether you find the distance between x and y or distance between y and x, it's same, right? And third is the most important, which is the triangle inequality, that is the distance between two vectors is less than or equal to the distance between x and the third vector z, and z and y, right? Yeah, so this is the one of the most important properties which appears everywhere almost, which is called the triangle inequality. Fine, this is called positive definiteness, and this is called symmetric property. So these three properties, if so yeah, so if I have a set X, and so D is a map from X cross X to R, specifically R plus union 0, right? Because the image should always be, yeah, once we define the map like this, we do not require this anymore. Fine, yeah, and which satisfies this property that the distance between two vectors is 0 if and only if they are the same vectors, and that these symmetric properties hold. And the triangle inequality hold, then we can say that D is a metric, and if I have a non-empty set with a metric defined on it, then we call it to be a metric space. That's the usual definition, and you can study a detailed course on metric space. You can go for reference books wherever you like. There are multiple reference books available. We don't require that much detailed notion here, though we will require the notion of a Cauchy sequence, but still rather it will be quite easy if you relate it with R. Okay, yeah. So what does the okay? So let us start with the definition of a contraction. Okay, so let XD be a metric space, and F from X to X be a map. We say F is a contraction. We say F is a contraction if the distance between Fx and Fy is less than equal to the distance between X and Y for all xy in X. Clear? Okay, so this is and it abides by the name assigned to it, right? Contraction. So we take two points from X, we measure the distance between them, we map them through F, and we see after mapping the distance decreases. So the mapping actually brings these two vectors closer to each other. It contracts the vectors. So the contraction, the name comes from there, and we say that it's a strict contraction. We say F is a strict contraction. In simple words, if the inequality is strict, okay, I have written it to be a striction, sorry, is a strict contraction if there exists some constant which is strictly between 0 and 1, such that the distance of Fx, Fy is less than or equals to C times dxy. In other words, we have a strict inequality for all xy in X, and this C is called the contraction constant. The contraction constant. Fine. Work out an example on your own. I'm not gonna detail it out. Let F be a map from R to R such that f of x is just x plus 1. Then you can check that it's a contraction, but not a strict one. And it's sort of evident from the map itself. Okay. Yeah. So since we are in R, just use d of xy to be the absolute value of x minus y. Fine. Now what is a fixed point? So a fixed point is a point which gets mapped to itself under the map. Okay. So definition. So we are assuming X to be a metric space everywhere. So let F be a map, and let X be in X. Then X is called a fixed point of F if F maps X to itself. Fine. Okay. Now, so this is the theorem, which is the contraction mapping theorem. Contraction mapping theorem. I guess this is also called the Banach contraction mapping theorem. I don't exactly remember. So let XD be a metric space. Let XD be a metric space, and let F be a contraction. But it won't work if it's just a contraction. For example, let me give the example itself here. If I choose the map fx equals to x plus 1, it has no fixed points, but we had seen that it's a contraction, but it's not a strict contraction. So for the contraction mapping theorem, what we require is a strict contraction. So be a strict contraction. Fine. Then f has at most one fixed point. Then f has at most one fixed point. Moreover, if x is non-empty and complete, that's what necessary, complete, then f has exactly one fixed point. Fine. And the proof is a bit technical but easy. Okay. So how do we prove it? Proof. Okay. What we do is the goal of the proof is how we try it out. See, let me first analyze the statement of the theorem, and then we will be clicking out things. See, the first thing is that we have f to be a strict contraction. Fine. So we will have to use the definition of a strict contraction somewhere. A very important word to observe in this theorem is that the metric space is complete. And what do I mean by a metric space being complete? That is, every Cauchy sequence is convergent. That means that we have to make use of the convergence of a Cauchy sequence, because that is the reason why we are given that the metric space is complete. So and from here it clicks some idea that how can we try that if I have a sequence which is in some sense related to this map f, which will eventually become Cauchy, so it will converge to some point, and that point might give you a fixed point. So if the convergent point should give you a fixed point, then this map must be recursively defined in terms of f, right? So what we do is that define a map for x0 in x, or rather let me start it in this way. Let x0 be in x, define a sequence xn recursively. Recursively by, so what we do, we define xn plus 1 to be f of xn. Okay, n is equal to 0, 1, 2 and so on. Okay, now observe, now d of xn plus 1 xn, this is less than or equal to, or rather this by definition is, it is d of f of xn, f of xn minus 1, and so this should be less than or equals to c times distance between xn and xn minus 1, right? So for some c less than 1 greater than 0, we have this. Fine. Yeah, so we have made use of the fact that how this sequence is defined recursively, and that we have a contraction, we have a strict contraction. Fine. Now we can observe it immediately that, so if I just keep going, see down this dxn, so this should be equals to c times d of f of xn minus 1, f of xn minus 2. So this will give me, so this should be less than or equals to c squared times the distance between xn minus 1 and xn minus 2. So if I continue this process, it will be eventually less than or equals to c to the power n distance between x1 and x0. Got it? Yeah. So once we have this, so this is actually the important fact to observe here and nothing else. Now c, and one more thing to observe here is the c was strictly between 0 and 1. We need to be clear about the fact that we are using every single hypothesis given in the theorem, right? Now if n is less than m, just consider dxn xm. Now you can easily observe that dxn xm by the triangle inequality, this can be written as d or distance between xn, so it can be written as distance between xn and xn plus 1, then so this should be less than equals to this plus the distance between xn plus 1 and xn plus 2 plus so on and so forth till the distance between xm and xm minus 1. So we are writing it in a way that it clicks good for us. So rather so this is less than, this is summation I is equals to n plus 1, right, to m distance between xi and xi minus 1, correct. But xi and xi minus 1, so this was less than or equals to c to the power n, right. So this is less than or equals to, what do we have here? So for I is equals to n plus 1, we have c to the power n, right? Yeah. So this is c to the power n plus c to the power n minus 1 plus, sorry, c to the power n plus c to the power n plus 1, so on and so forth till c to the power m minus 1, right. This times dx1 x0, correct, correct, right, fine. Okay, what can we do now? Yeah, so I can take Cn outside, Cn times, so this becomes 1 plus C and so on and so forth till or rather let me do one thing, let me just not just get into symbols and symbols. See, this will be less than equals to its infinite sum, right. So this will be less than equals to Cn plus 1 and so on, Cm minus 1 and continued, right, times dx1 x0. So now if I just pull out Cn, so this will just give me this sum, right. And since C is less than 1, so it gives me a convergent geometric series. So this is the Cn dx1 x naught into 1 minus C inverse, right. But then right, so C is less than 1, so as n tends to infinity this goes to 0, right. So since C is less than 1 greater than 0, C to the power n goes to 0 as n tends to infinity, which implies that dx and xm goes to 0 as both goes to infinity, or rather let me not stress line here, which implies that xn is a Cauchy sequence. Xn is a Cauchy sequence, fine. So given xn is a Cauchy sequence, now this implies, okay, now xn is a Cauchy sequence, fine. Therefore if xn converges to some point x, fine, or rather let me do it in this way. Now if limit xn does not exist, then f has no fixed point. We will see why is it so, or rather let me not write it like this, okay. Now suppose x is non-empty, which is somewhat we have already assumed because we have chosen a sequence out from x, so this is no more valid. Suppose x is complete, this implies xn is convergent in x, capital X. So let limit xn as n tends to infinity be x, right. Now since f is a contraction, this is very easy to see f is continuous with respect to the metric D. This is very easy to see, okay, just apply the definition of continuity and you are done, which implies that limit n tends to infinity, or rather f of x, which is equals to f of limit how should I write it, yeah, okay, so this is limit n tends to infinity xn, fine. This is okay, one second, yeah, so Yeah, so then this becomes limit n tends to infinity f of xn by continuity of f by continuity of f, but f of xn is xn plus 1, but then this is again x, right. Therefore f has a fixed point x is the limit of the Cauchy sequence. Therefore if x was not complete, then we had no guarantee that this Cauchy sequence converges, and in that case we had no fixed point. So if we have a fixed point, then there is at least one because of the uniqueness of this limit of xn, otherwise we have none. So that's where this completeness comes into existence. Fine, yeah, so that's the end of the proof. Fine, okay. Now one important consequence of the fixed point theorem, you see there are multiple fixed point theorems, okay. There is something called a Brouwer's fixed point theorem, which is studied in algebraic topology, where we say that if I have a function from Dn, that the n dimensional disk to the n dimensional disk is continuous, then it has a fixed point, okay. This is something, this is the Brouwer's fixed point theorem. Then we have something more interesting which is not exactly a fixed point theorem, but something which called fixed point anti-fixed point theorem. A more famous name of it is the Hedy-Ball theorem, and it's also sometimes called the Poincare-Brouwer theorem, okay. This says that if you have a function f from S2 to S2, that is the sphere, so how do we define S2? I guess you should know that is the sphere in R3, such that x square plus y square plus z square equals to 1, okay. If I have a function if is continuous, then it either has a fixed point, or an anti-fixed point, that is f of x equals to minus x, okay. Yeah, so you can also find a proof of this in any algebraic topological text, as well as I guess you will have a reference to this whenever you study manifolds in details, and I think you will also get a proof of it in any algebraic topology text. I don't exactly remember where I had studied this, but I had studied this. I get you will get a proof of it in topology by Armstrong. I don't think Munkres has this. I mean Hatcher has this. Okay. Now we come up to a very important consequence of this contraction mapping theorem. The reason why we studied this, which will be essentially used once we prove the inverse function theorem. Okay, that is why we are studying this. Okay, so let's see the proof. Rather let's see the theorem. So let B 0 R be a ball in Rn, the open ball centered at origin of radius r. So let this be a ball in Rn, and G be a map from this ball to Rn such that G maps the origin to the origin, and G is a strict contraction with the contraction constant being 1 upon 2. So here we are using the notion of a norm, and you can see that this actually defines a distance between Gx and Gy. So it's actually the metric itself, metric induced by this norm, the usual norm on Rn. Okay, and this happens for all xy in B0R. Fine. Okay. Then if I have this map f from 0R, B0R to Rn such that f of x is defined to be x plus gx, then this map is 1 1, that is injective, and moreover the image of the ball it contains the half ball, okay, the ball of radius r by 2. Fine. Yeah, so let us see a proof of this. The proof is again not yet difficult. See, first we show that f is injective, and the proof is again quite easy. Okay, suppose there exists xy in B0R such that f of x equal to f of y. Okay, then this implies x plus gx is equals to y plus gy. This implies gx minus gy is equals to y minus x, but this implies that the norm of gx minus gy is equals to the norm of x minus y. But the norm of gx minus gy, okay, let me do it in this way. Suppose there exist two distinct points x xy such that this happens, but so this implies that the norm of x minus y, this is less than or equal to half times norm of x minus y, which is a contradiction, right, because x was not equal to y. So therefore this is not possible. The distance between 2 points cannot be less than equal to half the distance between those, right. Therefore x needs to be equals to y, or rather therefore the only possibility, or rather we do not even require this assumption. Okay, so the only possibility which implies that norm of x minus y should be 0, that is the only possible case, which implies x must be equals to y. Oh, okay, let me not take the proof here. Yeah, so f is injective, right, f is injective. Fine. Now we show that the image of the ball contains the half ball. Okay, now let y be in B0 R2 R by 2 to show that y is contained in the image of this, which implies we need to show that there exists some x in B0 R such that f of x equals to y, right. But then what was the value of f of x, which implies that x plus gy f plus x plus gx equals to y, or which implies x equals to y minus gx. Does it click something immediately? Does it click something immediately? See, so what we have to do is that we have to equivalently prove this to show that there exists some x in B0 R such that f of x equal to y. But then this is just a fixed point principle, right. So which is thus we need to find a fixed point of the map x going to y minus gx, right. That will do. Once we find a fixed point of the map, in that case f of x, the image of x will be x, and that will be exactly y minus gx. So we are good to go. Fine. So how do we prove this? So let us define the map. So let f be a map from B0R to B0R such that f of x equal to y minus gx. Fine. Now if x is in B0R, then norm of fx is less than equals to, or rather norm of fx is equals to norm of y minus gx, which by the triangle inequality is less than norm of y plus norm of gx, right. Now y was coming from B0 R by 2, so its distance from the origin should be less than R by 2, right. So I can write it as norm of y minus 0, and since g0 is 0, I can further write it as this, So we have used the fact that that G maps origin to origin, but then this should be less than r by 2, right, because y comes from the ball around origin of radius r by 2, and this is plus half times norm of x, right. But then again norm of x comes from the ball around origin of radius r, so norm of x must be less than r. So this is equals to r by 2 plus r by 2, which is just r, right. Therefore f maps b0r to itself. Fine, it's good to go. Similarly, by the same argument, for some small epsilon, we can see that f maps this closed ball to itself, f, okay, for sufficiently small epsilon. Okay. So for some sufficiently small epsilon, you just mimic out the same argument. Why do we took the closure? Because it is complete, right, because it is complete. Okay. Now for all x prime in b0r, the norm of fx minus fx prime, this is simply norm of gx prime minus gx, but then this is less than or equals to half times norm of x minus x prime, which implies f is a strict contraction on b0r, hence on b0r minus epsilon closure, which is complete. Hence f has a fixed point. F has a fixed point, which implies that there exists some x in b0r such that f of x equals to x, which implies x is equals to y minus gx, which implies x plus gx is equals to y, which implies f of x is equals to y, and we are done. Fine. Okay, yeah. So let this lecture be up till this much. In the next lecture, we will come up with the inverse function theorem, which is a very important theorem to understand derivatives of invertible functions. And then we will be studying the implicit function theorem, and I'll try to stop this series itself in the implicit function theorem, but in some point between we will also talk about the how can we exchange second partial derivatives, which is something called the Clairaut's theorem. I might bring this in the next lecture itself, or rather in the next lecture we will talk about the inverse function theorem, because we have studied these prerequisites for that. So the next to next lecture might be on the Clairaut's theorem. Otherwise, after completing the implicit function theorem, we will come back to the Clairaut's theorem. It's just manipulating double partial derivatives. Yeah. So meet you guys in the next lecture.